In the last lecture, we looked at the digital abstraction, and we showed that this digital abstraction gave us tremendous noise immunity over analog signal processing. In the digital domain, we focused on two values, 0 and 1, and all our signals were comprised of just these two digital values. In this sequence today, we will look at what's inside a digital gate. Although you could go ahead and use the digital gate abstraction without really knowing what's inside, and that's kind of the beauty of the digital abstraction. As EE and EECS engineers, someone has to go and build those gates. And so let's take a look and see what's inside those gates. The reading for this section is chapter 6 of the textbook. Let's start with a quick review. So we looked at the digital abstraction, and in this abstraction we digitized values into 2, 0 and 1. We also established the static discipline, and in this discipline we all agreed that digital devices would meet certain voltage thresholds. And provided all of these devices met voltage thresholds, it's like speaking a common language, they could all talk to each other. So in terms of the global context of things, recall that we had our EECS playground. So here is our EECS playground. And within that playground, you have some region which is comprised of linear circuits. And all of the circuits are within EECS. So some region was linear circuits. And then we said there was this other region inside that we called a digital land. And within that, we had agreed to focus on just two values, zeros and ones, signals that comprised of just highs and lows. Now, within digital land, we can have sets of devices that follow a static discipline. So if a set of devices follow a static discipline 1, then you could think of all of those devices as being present inside this region of the playground within our digital domain. And as long as all the devices within this group followed a common set of voltage thresholds, then they would all be able to talk to each other. Now, a different manufacturer might go and choose a different static discipline 2, and a completely different set of voltage thresholds. So, for example, for a 0, they might pick 5 volts, while in a different part of the playground, a manufacturer might pick a 0 to be 0 volts. Now, both are okay, just that the two may not be able to talk to each other. So as long as devices within a family followed a convention or the static discipline, they would all be able to talk to each other. So in the static discipline, we have a set of voltage thresholds. So for example, if I have a sender and the sender needs to send a set of values to a receiver, then we expect the sender to follow a rigid set of values. So for a 1, a sender would have to send values VOH or above. And for a 0, the sender would have to send values that were VOL or below. Now, similarly, on the receive side, the receiver would have to interpret values VIH and above as a logical 1, and similarly values VIL and below as a logical 0. And notice that the difference between VOH and VIH corresponded to the 1 noise margin. Okay, so the voltage from VOH could droop down to VIH, and the receiver would still interpret that as a logical 1. Now, the region between VIL and VIH is an illegal region, and we call that the forbidden. And signals, and it's illegal for signals to stay in there for long periods of times, and the signals need to transition very, very quickly as they go through the forbidden region. So with the static discipline, I may have some gate, say for example a NAND gate, and so the outputs of the NAND gate would have to satisfy VOH and VOL. And similarly on the receive side, I may have some kind of an inverter, and the input of the inverter would have to satisfy the input voltage constraints. So then again, the outputs satisfy output voltage thresholds, and inputs would have to satisfy the input voltage thresholds. So these thresholds really are a specification on how we must design our digital gates. Continuing with the review, we looked at the combinational gate abstraction, and in this abstraction, we introduced certain sets of devices. For example, this is a NAND gate, and in these devices or gates, the outputs must be functions of the input alone. Okay, so at any given point in time, I can look at the output and uniquely determine its value by looking at the inputs at that instant in time. Now, this will be distinguished from other devices, such as memory devices, in which the values can be stored inside the devices, and at any given point in time, the inputs alone do not reflect what the output looks like. Second, these gates must satisfy the static discipline. So we also talked about truth tables, and so here is the truth table for a NAND gate, and the truth table enumerates all the outputs for a given set of inputs. So for example, if my inputs are 0, 0, the output is a 1, and so on and so forth. And for a NAND gate, the output is 0 when the inputs are both 1s. We also defined digital circuits, and we took a set of combinational gates and connected them with ideal wires, and we got digital circuits. So here is a digital circuit with 3 gates. We have a NAND gate, we have an inverter, and we have another NAND gate. Analyzing digital circuits is pretty straightforward. So for example, if you look at the output at this point, it is A ANDed with B, and there's an inversion happening. And similarly, for the output of the inverter, it is C bar because there's an inversion happening. And then we can write down D as A dot B bar, and that is ANDed with C bar. And then we take the whole thing and we put a inversion on top of the whole thing. So here is the a 3-gate digital circuit, and I've written down the output for you. So a lot of digital design is done with gates, or higher abstractions that are even more abstract than gates. So if you look at a microprocessor such as an Halem class chip from Intel, that, believe it or not, has on the order of 1 billion gates. Okay, a lot of gates in today's design. So it's close to 1 billion gates. The raw multi-core chip, designed at CSAIL at MIT, built by graduate and undergraduate students here, had about 3 million gates. And then if you look at the 64-core tile processor, that has on the order of 500 million gates. So notice that in these digital designs, we very routinely bandy about numbers in the orders of billions. Okay, we design circuits containing billions of gates. And the reason all of these gates can function correctly is because of the key noise immunity property that, as I connect a bunch of these gates together, each gate is cleaning up the input. Okay, if I get VIH and if I have some gate, if I get VIH here and say a VOL level value from some other sender somewhere else, then it is incumbent upon me that if I produce a 1, I have to produce a VOH, and if I produce a 0, I have to produce a VOL. And notice that VOH had tougher standards than VIH, and VOL has tougher standards than, I'm sorry, I should have said this was VIL. VOL has tougher standards than VIL, which I interpret as a 0. And so VOL is the tougher output that I have to produce. And so notice that there was a cleanup of the signals being performed, and each time the signal was processed, and that really gave it noise immunity when I have billions of circuits and billions of gates in a system.